Good morning, good afternoon, and good evening to everyone joining us from all around the world. Welcome to VTS Young Professional Webinars. We are delighted to have you with us today for an engaging and insightful session. I am Shadliya bin Naila, Secretary of the IEEE VTS Young Professional Committee and coordinator of the Young Professional Webinar Series. Today, we are pleased to host Dr. Haleem Farman, a researcher at Prince Sultan University and adjunct professor at Whitecliffe, New Zealand. Dr. Farman is a researcher with over 15 years of experience connecting academia and industry. He has led and contributed to internationally funded research projects and currently serves as vice chair of IEEE Smart Cities Awards and Recognition Committees. His expertise focuses on IoT, smart cities, cybersecurity, and artificial intelligence. We are delighted to explore his perspectives on securing the Internet of Vehicles, deep learning-driven intrusion with real-time missing data imputation. Without further delay, please join me in warmly welcoming Dr. Farman. And Dr. Farman, the floor is all yours.
Thank you. Thank you very much for the generous introduction. And thank you for inviting me for the talk. Today we will be talking more about the Internet of Vehicles that we all know about. Like these days we have the autonomous vehicles, and all these vehicles are connected to each other. So whenever devices are connected to each other, we will have the security problems and all these. So we'll be looking into some of the security aspects of IOV, and then moving towards like the problem statement, and then how we are going to deal with that. So this is a bit of introduction that was already made by the host. So I'll skip through it and just maybe I can just tell you about our international collaboration that we have, because without collaboration you cannot grow. So we have some of the international institute at our panel and some of the projects that we are working on. So moving ahead. Okay, in today's talk, we will be covering some of the aspects like from IoT towards IOV, as we all are aware of the Internet of Things. So how it's going to move from IoT to IOV, and then maybe a bit of introduction or a bit of talking about the traditional transport systems, because as we are talking about Internet of Vehicles, so for that the most important thing is traditional transport system and how we evolve from traditional transport towards the IOV and the smart transportation. And then some of the security challenges that we have in Internet of Vehicles, and then the main problem that we have in the real-time data that we are dealing with in IOV, that is the missing data problem. That's the main actually problem that we will be looking into it. And then the proposed IOV security framework that what we have proposed and how we are going to tackle them. And at the end, we will have some experimental scenarios where we are checking towards how the proposed framework is working by having different scenarios. And then at the end, we will have contribution and future scope. So as we all are aware of Internet of Things these days, we are hearing a lot about Internet of Things, and there are companies which are also giving the services of Internet of Things. And we are aware of that Internet of Things means that the devices are connected to each other, and it's not like a few hundreds, it's actually millions and billions of devices. They are connected to each other and they are sharing the data. And they are generating so much of data in real time even as well, and even offline, and that later on that can be shared through edge computing and through cloud computing. So we are witnessing this much of devices and its connectivity, and whenever there is a connectivity between the devices, we also know this thing that security concerns is there. And this is the case with the Internet of Things and the Internet of even vehicles even as well. And why this Internet of Things expanded actually in the past few years, and if we look into it from the past few years, so we know that there are cheap sensors. All the sensors that we have, they are like not that much expensive. It's a bit cheaper in comparison with the previous ones. And then there are embedded systems, so all of them are together. We have the 5G, 6G connectivity, and obviously for these type of devices, we do need connectivity, and the connectivity which has like a good bandwidth where you can send your data, and that data can be anything: images, videos, voice, anything that we are going to have. And then we have the cloud computing, which has given a boost to Internet of Things because of the connectivity, that you don't have to process the data or to keep the data at your local premises. You can share it with on the cloud or maybe through edge. So that's also one of the thing, one of the reason, I must say, that it give this IoT as this rapid expansion actually. And then we have AI, and AI is all we are aware of, that how AI is has evolved actually the all of the computation even as well. And the world, I must say that everywhere we have the AI, where you're using it for intelligence, you're using it for computation, for prediction, and all these stuff. So all these things has resulted in expansion to the IoT. And when we talk about the Internet of Vehicles, so it's, we can say it's kind of a specialized extension of the IoT, where we have IoT in generic, and then when we talk about the Internet of Vehicles, it's like a subset of the Internet of Things actually. So why IoT or IoV in fact became necessarily, because all, in this era we are all aware of that the devices, or specifically the cars that we have, the vehicles that we have, they are all embedded with sensors. Some have like few sensors, some have many sensors. You will have like so many sensors on one particular vehicle. So all these need to be connected, and then when it's connected to across each other, it has to send the data to another nearby vehicle, or it can be again through a cloud or through a central unit where it can be processed. So that's the reason that the IOV or has also been necessarily where these vehicles has to communicate, and it has to share the data of itself even as well, and the data nearby surrounding what's happening to it. It can share like the incidents that happening around it, or any information that we want to share. So it becomes really important when we talk about the IOV. And then we have this autonomous systems. We all are witnessing the electric vehicles, the autonomous vehicles, and they all require real-time communication with each other. So there must be infrastructure. It should be intelligent enough, and it should be integrated actually with the smart traffic even as well. The RSUs should be connected, and then the smart traffic infrastructure. So the thing is, they should be connected with each other to have a proper network where all these data can be shared actually. And then obviously when we talk about these type of connectivities, and like a huge amount of devices, they are connected to each other and sharing the data of each other. So there is a demand for the safety as well of the drivers as well, of the pedestrian even as well, and overall the security of all these data that we are sharing as well. And at the same time, we have to make sure that it is efficient even as well. So, before going into the IOV, we all are aware of the traditional transport system that we have actually, because when we talk about the traditional transport, so it's like the individual, they are being characterized. It's a disconnected modes of the transport. You are manually controlling each other. There is no like proper control of the traffic. So they are like more reliance on the fossil fuels. There is no like intelligent what we call it, the management of the energy. And then we have the road centric and infrastructure heavy. We are all aware of it, and we have the limited integration of all these mode across each other. So, keeping in view this traditional transport, as it has some key challenges as well, and we are aware of this thing, that the most important one is the traffic congestion that we all are experiencing, specifically in the urban areas that we are living in. Then the second one is the safety concern. Obviously, the high accident rates, it's out there, so it's really important to have a look into these safety improvements even as well. And then we talk about the environmental impact. So we all are aware that like these car can produce so much of pollution that can be really hazardous to the environment. So we have to take care of the environmental impact as well. And then the unsustainable economics, that rising fuel cost and all these things, it's like more towards the unsustainable energy. So these days we are witnessing the electric vehicles that are more like towards the battery and all these stuff. So there are so many other challenges obviously as well. But when we talk about the main challenges we are facing, and we are having these challenges when we talk about the traditional transport system. And here comes the IOV then keeping in view all these challenges in the traditional transport system, we have the advent of the Internet of Vehicles, where all these vehicles on the road that we have, they are connected to each other and they are sharing some useful information with each other. Even like the sensors that we have in a particular vehicle, that also needs to be connected, where we can control even the information of a particular driver on a particular vehicle even as well, and then later on it can be connected to another vehicle, and it can be connected to the roadside units that we have, and it can share the data over the cloud or over the edge for further processing and for any other things. So that's why it's really important to have the Internet of Vehicles. And we usually, when we talk about the Internet of Vehicles, overall broadly we call it the smart transportation, where IOV is the backbone of these smart transportation. And we know that everything is becoming smart and connected. As the new vehicles, they are equipped with so many sensors that even if you are driving and you are parking your car, so it will give you the obstacles that nearby in through some sensors even as well. They are embedded in the rear and the back of it, of the vehicle. It can detect the object, and it can give you an alarm. Even if your speed is crossing from a particular limit, it will give you an alarm. And if, let's suppose, a driver is not moving the steering or something for a while, it can give you an alarm. So there are so many features that we are witnessing, and we are having it in one particular vehicle. So, what are actually the enabling technologies when we talk about the smart transportation? So, the most important one, in fact, all of them are important, to be honest. Like one of them is the smart vehicles, and when we talk about the smart vehicles, means the vehicles are connected to each other, they are sharing information with each other. Then we have the AI powered self driving technology that we are witnessing these days as well. By using the AI and machine learning algorithms, they are being deployed over there, and the car can move autonomously. And we are witnessing the electrical vehicle even as well these days. And then one of the most important thing is the artificial intelligence that we are using. We can use this AI for the congestion management, for the real time traffic monitoring, and even for the decision making, like depending on the traffic pattern and all these things, we can predict what exactly traffic is going to be in a particular time and a particular road. So it can really improve the decision making of the government, of the local government even as well. And then we have the mobility as a service, where we have these integrated transport platforms, where we are using, like for example, the buses, the metros. We are using the ride hailing, the bikes, and all these transport needs to be integrated. So there are apps available which can seamlessly integrate into each other, and it can give us all these solutions, I must say, towards this seamless payment and ticketless ticketing solutions that we talk about. And then we have obviously the smart infrastructure and connectivity, because that's really important when we talk about these Internet of Vehicles and smart transportation. So the most important thing is the infrastructure. If you have the infrastructure which can really support these this phenomena, and we must have the connectivity even as well. So for that, you need a good bandwidth in order to, or a high bandwidth in order to have these connections, and then to share the data among the devices even itself, or with the vehicles, or with the infrastructure. So the 5G 6G connectivity is already there, and it's been already witnessed to have the low latency, and to have the integrated mobility for the responsive urban transportation. And then we have the Internet of Things, where all these sensors, they are being connected to each other to collect the data. It can be, again, as I mentioned earlier as well, it can be different types of data, different types of sensors are available that are responsible for different types of data, to actually to enhance the experience even of the driver itself, even, and even to have the to experience of the surroundings even as well. And the most, what we can say, like one of the modes, there are different modes, obviously, of communication when you talk about the vehicle. So if the vehicle is on the road, it has to communicate with the network, which we call to the V2N communication. And it's been most right towards the real-time traffic and routing, or the cloud services that we are talking about. Then vehicle-to-vehicle communication is also there when we talk about the Internet of Vehicles. So it is mainly for the collision avoidance and for the safety systems that we talk, because if the vehicle is coming near to you, so it can give an alarm, or it can detect, okay, there is an object or a nearby vehicle. So the driver has to be really on toes to have the precautionary measures. And then we talk about the vehicles to the infrastructure, which is really important because these vehicles, they have to share this data with the infrastructure in order to send it to the central unit or maybe to the cloud for further processing. And even like the traffic signals, the timings of it can be shared. So the traffic signal can also even communicate to the infrastructure. And then we the one of the good one is the vehicle to the pedestrian. So that's actually really good for the safety alerts to the pedestrians or to the bicycle or to the motorcycles, to have these alerts that they should be safe enough. So the vehicles can communicate with all these different modes. And the benefits that we can have from these is obviously to enable the communication between the vehicles and the roadside, which is the primary and the basic connectivity that we need in IOV. And then the real-time traffic information, the safety warnings, and the traffic signal optimization. And there are so many other benefits which we have from all these communications. So when we have the communication, obviously, if different devices are going to be connected with each other, and the vehicles are connected with the vehicles, it's connected to the pedestrians, to the roadside units, and all these stuff. So obviously, security will be there. And one thing that I always say that when devices are connected to each other, even if two devices are connected to each other, the security concerns are there until and unless that particular node or a device is an individual or a standalone device. Security concerns are also here in IOV. We have like the network can have, because the Internet of Vehicles, it's of a different nature, I must say, because of the mobility that we have, because of the speed that the vehicles are going. It can have different speeds as you are on the road. The vehicle is on the road, so obviously it will have different speeds. So that's one of the challenge, because the topology changes very dynamically, and then the connectivity is there. Like sometimes you are connected to the network, and sometimes you lost the connection and all these. So to have that problem, the intermittent connectivity, that's really a big challenge. And then we want to have the real time data transmission, because we want to have the data, whatever it's sensing, it should be sending it in real time actually. So that's also one of the challenge when you are on the move and you are sending the data to the roadside unit or even to the vehicle. So that's also one of the challenge which the IoV networks are really facing. And there are some other problems even as well. So when all of these problems actually, or the network that it faces, we have some common attacks that usually happens in the network. The denial of service attack is there, where the service can be disrupted, and the intruder or the attacker can really flood the network, and it can really jam the network or the signals over where we are connected actually. We can have the spoofing attack. Again, the impersonation can be there, or the fake signals can be generated to have the false alarm or all these type of things. And it can, let's suppose, divert you to another direction if you are going in one direction, and let's suppose if it's been compromised, so you will be given another direction. So that's also one of the things that can happen. Then we have the cyber attack, we have the data injection attack. Again, these are the different types of attacks that can happen whenever we are talking about the networks, and then particularly it can happen in the Internet of Vehicles even as well. And we should be like very much aware of these things, that the security failure in such type of networks can directly impact the road safety as well, and the human lives even as well. As let's suppose the devices or the driver itself, like if it's more depending on the data, so it can really happen. So we have to really take care of these challenges. But at the same time, these IOV, they also support the smart signals. We are also witnessing it. The emergency vehicle prioritization, it's there, predictive traffic control, the fleet intelligence. If we can look into this diagram, here we have like different, again, the connectivity can be to different technology, but these smart sensors or the beacons that we have, it can be cameras, it can be beacons. They are connected to actually through LoRa communication, again, depending on the technology, whatever you are using, and depending on the infrastructure which we usually have. But usually these days, the LoRa has been a popular one that's been used across these scenarios. And then it's been shared with the LoRa cloud. So we can have this data. It's been we for the data analysis, we will have the machine learning algorithms, and then the intelligent traffic management system is there in order to intelligently manage the traffic lights or the traffic signals, I must say, depending on the situation of that particular route or the road that we are on actually. So all of them should not be like same, but it depends on the traffic, or it depends on the congestion at that particular time. So one of the problem that arises whenever there is a connectivity, and since we have talked about the network that faces the problems of this high mobility and dynamic topology, it can have some missing data as well while during the communication. So the why actually this missing data occurs? That's the most important thing. So as we discussed in the previous slides, that due to this dynamic topology, packet losses are there. Again, it's due to the mobility. So that's one of the important and one of the most frequently thing that happens due to this. The data can be missed actually. Then we have the network congestion, we have the signal interference, we have the sensor even malfunction. Due to all these things, that we can have this missing data. And if the data is missed, for example, so that means that you are not transferring the whole information. So that can really have an impact on the overall decision that you are going to make. It can lead even towards the road safety or the human lives even as well, depending on the scenario and depending on the data that it has lost. But the data missing or the data loss is there actually. So when we talk about this IOV, it's more like frequent that we will have this data missing because of the mobility that we have. And the impact can be, it can increase actually the false positive rate. That's really an alarming thing. And then obviously the intrusion detection can also be compromised if we have this missing data. So one of the things that we will be discussing it in more detail, that we have around we have introduced the 20% of the missing data into the this real world, just to meet the real world conditions actually. So we have introduced the 20% of these missing values in order to mimic the real world conditions. And how we did that, we will be talking about that in the coming slides. So one of the research problem that we have addressed, or in this we will be talking about, that's the use actually most of the IDS research that is in the literature. They're using the clean bench data set, like there are no missing values, nothing. But in reality, when we talk about these data sets or the data that's been coming from these vehicles, as I mentioned, that different type of data is coming and at different timings. So it can have some missing values because of the dynamic topology, because of the signal loss, because of the network congestion. Maybe there can be different reasons in order to have the packet loss actually. So that's actually one of the things that we have looked into it. We have introduced some of the missing values to mimic actually the real world examples actually. Yeah, so benchmark data sets, they always remove the missing values during the pre-processing, which in our case it's not this is not in our case it's not happening. But in reality, yes, it has incomplete data streams as well, some dynamic communication gaps even as well, and then the limited research, yeah, on the real-time imputation in IOV. So the problem statement that we are looking into it, as I mentioned, that we should have such an IDS system that should remain robust while we are talking about the real-time vehicular data, and it will have the missing values in the real time, or the data that's coming from the network. So it should be robust enough to entertain or to tackle that. So we have introduced a deep learning based IDS system that can really work on this. So why deep learning? Why we have chosen the deep learning? As we know, like AI is doing a lot. So it actually learns complex non-linear patterns, the patterns that are coming out of the data. So it has the capability to detect unknown attacks even as well, depending on the data or the pattern that it has, depending on the training, that what exactly data we have given, it will be trained accordingly, and then it can detect the unknown attacks even for you as well. And then it handles the high dimensional data, because the data that's coming out of it can be video, audio, it can be images, it can be text. So it can handle this different types of data with high dimension even as well. And then it adapts to the dynamic environment, as I already mentioned. So some of the possible models, there are obviously so many, again depending on the situation, depending on the requirement. We can have the CNN, that's more like for the traffic pattern extraction. We have the LSTM, GRU. We have the autoencoders. There are some more different DL models that people have used. Like in the literature, we have witnessed that there are some different deep learning models that have been used in order to tackle different problems. So in this, we have actually proposed, or I must say, the proposed framework. Actually, it has two phases. One of them is the context-aware security with GRA. We have used GRA with the context-aware, and the other one is the content-aware security. And we will be talking about these in the coming slide, that how we have used actually these. So the phase one is the content-aware security. If we look into this flow chart, we can have on the right side that we have nodes. So for every nodes, the data that it's actually for the communication authorization decisions, we have used GRA for it. So whatever data it's coming from the nodes, it will compute the trust value. And for the trust value, we have to compute, or we have to compare actually these computed values with the predefined trust value that we have identified through the GRA. So it will look into the threshold. If the threshold is, let's suppose, less than, it will be labeled as the black node, and it will be completely denied or dropped. And then we have the other one is the white node. If it's the trusted one, means the value is more than the threshold, that it's allowed for the communication, and it's the trusted node, we can say. The most important one is the gray node, where we have done all these computation. That is only for the node, for the gray, because for the black and for the white, it's very much obvious. If it's less than the threshold, okay, it can be malicious node, it can be the trusted node, the other one. But what if, let's suppose, if the system is uncertain about, or it's like a kind of suspicious type of node. So for that, we have labeled it as a gray node, for where we will have the content based scanning. And that's is basically done through the proposed model, and then to re-evaluate for the security inspection, because these gray nodes can believe it's a white node, or it's a black node, means the malicious or the trusted one. So the criteria that we have for it, it's been a weighted one. It's been compared and then ranked based on some trust levels, where we come up with this threshold values. And then the other phase of this proposed framework is, like, we have as CNN actually. So whatever the gray node is, if it will be passed on to this proposed model, IVM CNN. And then here we are going to have the content aware security actually to address this issue, whether it's a gray node, or it's a malicious, or it's a trusted one. So for this computation, all these, what we have done, we have used different data sets actually. So one of them is the benchmark one, which was the UNSW and B15 data set, and we have used it like for the threats, or the attacks, that we have used this data set. And then for the other one was the augmented AB data set. So this was kind of an advanced version, in because of the fact that it has more feature than the UNSW and B15 data set. So we have used these two data set in order to come up with the effectiveness of this proposed model towards these IoT threats. So here we have like a bit of because as I mentioned, that this proposed model is going to inspect the contents actually of whatever we are getting, and then to evaluate the different type of attacks that we are having. So this IMV MCNN has this capability in order to come up with the decision. And here is where, like, the comparison with NSL KDD data set even as well. We have done some of the comparison, which we will be talking about in the coming slides even as well, that how we are going to have these data sets. But the main data sets that we have targeted, that is the UNSW and B15, and then the augmented AB data set as well. Some of the missing data handling techniques we have, one of the most popular one, or the most being used in the literature even as well, that is the KNN, the K nearest neighbor, and that was actually used to actually impute the missing values by identifying the K most similar samples. Again, it works on the Euclidean distance, and then replacing the missing entry with the mean values in order to have the nearest neighbor to find. That's like the typical approach of the KNN is on, in order to have the missing values and then the mean of it, and then you impute these values into that, and that's how it works. And then we have the iterative singular value decomposition, ISVD. It's also been used for the estimating the missing values, and it works as an iterative actually matrix factorization, where we have this data matrix. It's been decomposed and then updated repeatedly until the missing entries coverage to a stable approximation. And then one of the technique that we have proposed over here, that is the proposed smart imputation technique. So this smart imputation technique, it has actually intelligent reconstruction, and that means that this technique actually it reconstruct the missing values actually by learning the patterns from the complete data that we have, and then estimating that okay, the accurate replacement of these values, based again on the feature relationship obviously. And then we have this again, this proposed method, or this PSIT actually, it reduces the bias even as well by filling the missing values. You will by using the learn feature, the learn feature relationship that it has, like instead of deleting records or using random replacement that usually we have in the literature. And then obviously overall it improves the performance even as well, by supplying the complete and consistent data to the model for efficient or to enhance the classification results that we have. So how this PSIT actually works? Again, the proposed smart imputation technique actually, it's a robust framework to intelligently handle the missing values within the network, or within the network, that whatever data we are getting from it. So we will have like the full data set actually, and then in the full data set we have like it's been trained and evaluated again using the NSW data set. We have used it on the, as I mentioned, the benchmark data set, where 20% of this mobility induced is because of the fact that it should be more simulated towards the real world environment that we have, because in real world we will have these missing values, and normally in the literature, in the data sets, it's been in the pre-processing, these missing values have been removed and the data has been cleaned. So this is not the case over here. We are actually inducing these missing values just to mimic it with real time, so that it can, the model overall, it can work well in the real world whenever we are deploying this model actually. And it's actually to generate or to have this realistic missingness, actually we have used one of the function, that's the missing pattern function, where we are using actually even the random numbers even as well. And so that's how actually the overall PSIT works. Here the flow chart is there, where we can see like if there is a missing data. So if it's yes, so obviously it will fill these values with the missing values, again using PSIT, and then it will gather all these missing values and have one complete data set. And let's suppose if it's no, so again it will go towards the it means that it is the complete data set DDS. So it will train and test again the NCNN model, then evaluate accuracy, and then whatever like the confusion matrix we get, or whatever data we are getting from it, it will print it for us. So this is just like a flow that how exactly this works. So the data sets that I have mentioned already that we have used in this work, that was UNSW, the benchmark, and then the augmented ABI set. We have used actually the augmented ABI set, that we have increased the number of features. Actually, it was initially 49, and we have increased it to 194 features, because the more features we have, the more accurate results it can give to us. And that's how we augmented the ABI data set from 49 features towards the 194 features. And how these feature augmentation process works. So again, original feature that we see in the flowchart even as well. It was presented by FORIG. It means the feature original, and it's the X1, 2, 3, and X, and these are the features actually. And then for each of the feature, it has to check whether it's in the original or not. Then we have to modify slightly modification or slightly modified values that are being generated using the small positive and negative perturbation actually. So these just are added to the new augmented set, and then that's what we call it. The F augment means it's the augmented features actually from 49 towards the 194. So that's how we have like increased it, just to have like the more features you have, the more efficient performance it will have. Some of the experimental scenarios actually, that's we have actually. Scenario one was that we don't have any missing value, no missing data is there. So the model was trained on the benchmark data set, and then we have like the trust models where we have these input values, and then there is a trust model. We have the entity oriented model, we have the data oriented model, and then we have combined it to the hybrid trust model. So this is actually the context security thing, and then it passes on for the decision. Let's suppose, as we mentioned, that if it's a black data, means if it's a malicious node, so it will be dropped. If it's a trusted one, it will be towards. If the white node, if it's a white node, it means it's a trusted node. And if, let's suppose, if it's a gray node, so that the whole process is actually depending on the type of the node that we are getting from the context security. So for the gray node actually, we have used this multi-CNN architecture, where we have these fully connected layers, and then it's the multiple activation functions being used, and then at the end it has to give you the result, whether it's a benign, the generic, exploit further, the DOS, what type of attack it is. So this is the content part of it. So here in this scenario actually, we are not using any missing data. It's as it is that we are getting. Then in this scenario, what we did actually, we introduced the 20% of the missing values, just to mimic, as we mentioned, as to mimic as per the real time or the real world data that we usually use, you usually get from the network actually. So again, the first part is the same. As we can see, the input data is there, the trust models, and then we have to make the decision on it. And if it's, let's suppose, a gray data, so there comes the multi-CNN architecture, where it's basically looking into the data itself. So what we have done, that we have used this data set with 20% of the missing values, and then we applied some of the imputation techniques actually, as I mentioned, that KNN, ISVD, and PSIT. All of these have been applied on the data set, the imputation techniques, and then these imputation values, if we look into the right side, we have these imputation values from all these three data set. Then it's trained on again this UNSW data set, and then it's been given to the multi-CNN architecture to and applied some of the activation function that we have, the ReLU, sigmoid, 10H, and the leaky ReLU and softmax, all these, and to in order to identify which attack actually we have. So this intelligent imputation actually combined with this deep learning, it overall it improves the robustness, and it reduces the false positive rate that we are getting in the normal scenarios. And the third scenario was to check it on the augmented data set, because in the previous we have checked it on the UNSW one. Here we have used the AB data set. UNSW have 49 features. Here we have the 194 features, where we have increased actually these features because of the fact that in order to have like a more accurate result. So again, the first part is the same, and then when we look into the upper part of this diagram, we have the AB data set with 194 features actually, and then we have used the pseudo random generator with this data set, and then it's been passed to this mode actually, in order to have the balances between, because majority of the class we will have, and then we have the minority class as well, to have the balance between these two classes. We have used this mode for it, and then to have one complete data set with a complete what we call it, the same number of classes we have, and then we train again our model on this data set, and then we have again the multi-CNN architecture along with the activation functions in order to identify the attacks actually that we have. So these were actually the three main experimental scenarios that we had, and then coming to the results that we have from this. So here we can see the performance availability parameter that we have. So overall, we are getting around 83, 84% percent of the accuracy, while having the first scenario where we are using, like, there was no missing data in the scenario. So here we can see the accuracy is like satisfactory, but it's not at the high side. Then at the second scenario, where we used UNSW data set with some 20% of the missing values in order to check or to mimic the real world scenarios. So we checked on into the three imputation techniques that we use. And here we can see, like, the accuracy, it improved around, it's around 87. So it's from 83 to 87, it's improved like a lot. So because of the fact that it's like almost mimicking the real world scenarios. And then in the third scenario, if we look into the third scenario, here the accuracy is like more improved. It's in the around 90s, 91 percent, because of the fact that the features that we have used in the AB data set, that was like from 49 towards the 194. So it's a lot. So because of the increasing the number of features that we have, it has increased accuracy over as well. So we can say that the third scenario is more like suitable for mimicking the real world scenario that we have. So at the end, what contributions actually we have in this? So integration of the real-time missing data that we had in the IOV, then the extension of this IoT actually ideas into the IOV environment that we have. That we have used the CNN based intrusion detection, and there we have used like the two phases of it: the context aware and the content security integration. And due to this increasing the features, we have like managed to reduce the false positive rate. And then obviously we can easily it can be scalable for the 5G 6G smart mobility if we are going to deploy it, because it's a simulation based work that we have used. So if we are going to we can have it on the real environment even as well. And in the future work, actually, yes, obviously every work has improvement, and it has to be improved actually. So we can have the edge AI deployment in the vehicles as well, and we can have it in the real world deployment even as well, to check the accuracy of our model in the real world scenario even as well. And then we can use the federated learning for the distributed AI IOV actually. So we are aware of this thing, that IOV works in a distributed manner. So federated learning can be one of the aspect that we can have in this work to in order to enhance it more. And obviously we will be it can be integrated with the autonomous driving systems. When we talk about these connectivity, and we talk about the intrusion detection, so this can also be integrated with the autonomous driving systems. And then explainable AI, explainable AI can also be checked for the vehicular trust. So yes, this work has a lot of improvement to be done. In the future we can enhance it more by integrating all these things. And yeah, thank you very much for listening. And if there is any question, I'm open to that.
Okay. Thank you very much, Dr. Haleem, for the very interesting presentation. Uh, I would like to have some few questions actually.
Yeah.
We're gonna start from the conclusion. You were talking about the integration of your system within the autonomous driving. Can you explain more? Like how can you think that the proposed system can be integrated actually for autonomous driving?
Yeah, actually, the point was that in order to integrate with the autonomous system, because we are aware of that the autonomous system, they are well equipped, they have like more computation even as well. So because these devices, if they are connected with each other, these sensors, and if these vehicles are connecting or communicating with the other vehicles even as well, so obviously the security concerns can be there. So what we are doing, like, we can actually again, it's a future work, so we can integrate our framework into the existing autonomous systems or autonomous vehicles, because if it has a bit of more complexity, for example, so because of these vehicles, they don't have the complexity issue in terms of the computation power that they have, so it can easily be integrated. Again, time will tell, and if we are going to integrate it with it, how efficient it can be. But that's what we think, that it can be integrated with the autonomous vehicles.
Okay. Thank you. The choice of this model, if you can give more insight actually to our listeners, like the choice of this model. I suppose in the literature there are other models. Why did you choose this, particularly the IMV MCNN model? Can you expand further, please, on your
Yeah.
choice? Yeah, please.
Okay. So actually, the reason behind this is actually when you come up with a framework. So obviously, you would have done so many of your homework, maybe, or so many of your testing on other models even as well. But the thing was actually with this with IMV actually CNN. It was if we look into this one here, I can maybe yeah. So actually it is the imputed missing value. Imputed missing value, the IMV stands for that. And that was actually because we are actually explicitly imputing the values into the data set. So that was actually one of the things that we have named it IMV. And then the multi convolutional neural CNN is like a normal network that we are usually using. So we are using the multi CNN because of the fact that it's checking while when we talk about these scenarios actually. So we are actually having this multi CNN architecture involved or being combined with the IMV to have one overall framework that can look into the what we call it, the IDS, or to the intrusion detection system that we are developing actually. So that's why we have come up with these three experimental scenarios just in order to check how exactly this model is or it's working actually.
So, and following the presented experimental data, experimental results you showed earlier, we see that the efficiency actually is improved from scenario number 1 to number 3 with 91 actually.
Yeah.
Yeah, you could reach that.
Yeah. So actually, this
I
was yeah.
Yes, yeah, please. Yeah.
So it was actually due to the fact that because in this scenario, in scenario three, we have increased the features from 49 to 194, and that was because if we have more features, we will have more efficient result. You can like have like more detailed patterns, and you can look more detail into the data. So that's why it has improved.
Yeah, indeed, yes, as you explained it. I would like also to ask about the choice of the data set. You talked about AB and MB15. Are there any other data sets that can be applied
Yeah,
for this?
exactly. Actually,
Yes.
yeah, that's a valid question. Actually, we have used two data sets, UNSW and B15. That's a benchmark data set that we have. Then apart from this, there are some other data sets even available in the literature. So why particularly this one? And the other one is the augmented AB data set actually that we have used. So this is the augmented actually AB data set that we have used. It was because of the extension or the expansion of the features that we have, and the UNSW is the benchmark. So that's why we decided to have one benchmark data set, and the other one that's been developed like, or we have due to this expansion, we named it as the augmented AB data set. So this is, you can call it's like our own data set that we have used. So one of them was the benchmark to check our proposed framework on this benchmark data set, and the other one was to have it on the data set that we have augmented.
I see. I see one attendee to our webinar today. So I see Hannah attending. I'm wondering if she is willing to ask one question. I can open the floor for her. Hannah, can you hear me? I'm afraid not. Anyway, if you can hear me and you are willing to ask a question, please just mute yourself and feel free to ask a question. From my side, due to the lack of time, I will be maybe adding one. I have one question actually. One more question.
Yeah.
Can you explain this difference of numbers? So we started from 81, 83, and finally 91. Can you further explain to which the reason behind actually this improvement.
Yeah, let me have the result actually. Yeah, maybe I can explain it to the over here,
Yes,
because these results are from these scenarios. We have scenario 1, scenario 2, and 3. In scenario 1, we have views that we are not using any missing data. Like, there the data set is in a sense that we usually, it's a clean data set, you can say, where it has no missing values, right?
yes,
So that's why, but as I mentioned, that when we talk about the real world examples, the data that we are getting from the network, obviously it will have missing values, right? So we should
yes,
not ignore the missing values. That's the main purpose of this work. Is we should not ignore the missing values, because if we are going to train any model and there is no missing value and you train it, which we usually do actually, because we remove the blank or the missing values from the data set in the pre-processing phase, and then we train and then we test the model, right? That's the normal
yes,
thing that we usually do. But the point over here is to include the missing values. Don't ignore them, because in the real time when you are going to deploy it, so these missing values will come, and then you have to deal with the missing values. So it can actually affect the performance of the model or the accuracy of the model. So it can lead maybe towards the false positive rates and all these others, right? So that's actually
yes,
the main idea. So here, if we can see, in this scenario, we don't have any missing values, and that's why the accuracy was 83%, and it was increased to 87% because of the fact that now we introduce the missing values and we are mimicking it with the real world example, right?
yes,
So
yes,
that's how the accuracy was a bit improved and then we are checking it through these three different imputation techniques as well, by checking it through KNN, the ISVD, and then our proposed one, the PSIT. Okay,
yes.
so that was the second. And then in the third one, actually, because in third one we increase even the feature as well. 20% is there missing data, and then we increase the feature of the data set to 194. So when you
Yes.
have more features, it learns more, it predicts whatever you are predicting, and then it overall it has an impact on the accuracy that you have.
Yeah, indeed. And it makes sense, like when you, as you stated in your conclusion slide, you are talking about as future work is to the real scenario
Exactly,
deployment.
exactly.
So with the model taken into consideration all the missing variables, it seems that the efficiency for a real scenario deployment is quite high, to my understanding.
Yeah.
Thank you very much, Dr. Haleem, for your presentation. And we come to conclude our webinar today. So again, thank you for the insightful presentation on securing the Internet of Vehicles through deep learning, based intrusion detection, and real-time missing data imputation. Your work highlighted an important step actually toward building more secure and resilient intelligent transportation system. As you know, the record of our webinar will be available as usual soon on the VTS YouTube channel. Thank you again,
Thank you
Dr.
very much.
Haleem, for your availability today. It was a pleasure having you today. Thank you very
Thank you
much.
very much. Thank you very
I
much
wish you all the best.
for
Yeah,
hosting and inviting. Thank you very
thank
much.
you very much. Wish you all the best in your future endeavors. Thank you.
Thank you.
Thank
Thank
you
you.
very much.
Appreciate it.
Thank you.